All right, back from break. So, again, here is this remarkable story of communicating through setting up electric and magnetic fields, allowing them to propagate away from a source for those electric and magnetic fields, and then having those electromagnetic fields reproduce whatever signal we have used to generate them. And again, my favorite radio station, KQED. All right, so let's look at a couple of examples here. Here's one. It's a cell phone antenna. What they're telling us here is, I got a cell phone. The antenna inside the cell phone is often 1/4 of a wavelength. So by making the antenna 1/4 of a wavelength long is actually an efficient way to be able to pick up the signal that's being transmitted. Now the cell phone has an 8.5 centimeters? That's not possible. Okay, I'm not sure what era this is from, but 8.5 centimeters, that would be like this. Oh, maybe. It's going to be like between 3 and 4 inches. All right, maybe that's possible. So we'll say that there's an antenna hidden inside my cell phone, and it is 8.5 centimeters long. Let's estimate the frequency that's being used. So what they told, oh, that's a short answer. It doesn't take much in the way of calculations here. So what they said is the length of the antenna, 8.5 centimeters, and then they gave us an important piece of information saying the wavelength that we're actually trying to pick up with this antenna is going to be 4 of those lengths. And that puts us at 34 centimeters. And then to get the frequency that's being used, so they're using frequency here. We could have just left it at wavelength and said the wavelength is 34 centimeters. So that's kind of the wavelength that we're working from. I can take C. Now C is 3 times 10 to the 8th meters per second, but I put this in centimeters. So I made that 3 times 10 to the 10th, and then divided that through by the wavelength, and what that gave me was 882 megahertz. So I'm not sure, I guess I would have to go and check and see what range of frequencies have been allocated for cell phone communications, but I'm guessing the number that we've come up with is allowed by the Federal Communication Commission, FCC, whoever they are, that allocates the different ranges of frequencies for different use. Okay, well, those are the kind of problems you want to see show up on the midterm, right? All right, now measurements of the speed of light. This is kind of an interesting topic, and in fact, in our class, we'll be doing a measurement of the speed of light here in a few weeks. So if we haven't already done it, I think it's still a few weeks out in our future. There are different ways that the speed of light measurements have been done. I'm not going to go into detail on these. The one that they have here was some that were done in Southern California, using Mount Baldy and Mount Wilson. What I did want to refer to here is the earliest measurements, the earliest kind of reliable measurements of the speed of light came from observing Jupiter's moons orbiting Jupiter. And this dates back to like I think it's the 1700s. Galilei had discovered that Jupiter had 4 large moons, and so from the early 1600s, astronomers had been following these moons of Jupiter, and as timing devices got better and better, they could time these orbits, right? You get your telescope out, and you see in the, every evening that you can, when it's clear, you mark down, do some careful measurements of relative to Jupiter, where are the moons located as you're watching the moons move back and forth as they orbit Jupiter. So from Earth, they just look like the moons are going back and forth, and we understand that to be a roughly circular orbit. So what astronomers realized was that their timing measurements had gotten good enough again, I think this is like late 1700s, they had gotten good enough, or mid 1700s, that they could actually, over a period of months, observe that the periods of the moons, the time it was taking for an orbit, was taking a little longer sometimes, and other times it would be a little shorter. Now, these physicists, these astronomers, astrophysicists, realized that the orbits were the very same period over and over, so they asked themselves what could be happening in their observations, and they realized what they were seeing was the delay effect from the speed of light. So as Earth orbits the Sun, Jupiter's way out there. It's like 5 astronomical units from the Sun. The Earth is defined to be 1 astronomical unit from the Sun, and Jupiter's like 5 times as far away. And so as the Earth orbits the Sun, and Jupiter's orbiting much more slowly, sometimes Earth is farther away from Jupiter, and other times it's closer. And so what would happen over the period of the year is you could see that those periods of the orbits were getting longer, and then they would get a little short, not by much, just by a little bit. I want to say, well, how long does it take light to reach us from the Sun? It's like 7 or 8 minutes, right? And so the differences would have been no more than double that, maybe 14, 15 minutes variation during the entire year. But that was enough that they could actually measure that carefully, and once they had done that long enough, they could sit down and calculate, not with their calculators, but with slide rules. I'm not sure what calculating devices they were using. Maybe slide rules had been invented. In any case, they were able to measure the speed of light by the time delay of light coming to us from Jupiter, from Jupiter's moons, and they were accurate to within like 5 or 10%. It was actually a very good measurement of the speed of light, and now we've measured that much more carefully. So it's kind of an interesting history as to measuring the speed of light, and again, we'll get to do that in our lab, so you can take a look at the lab and see how we're going to be doing this. Now, the speed of light measurements have gotten to be so good and so careful that we now feel like our measurements of the speed of light are the most reliable method for defining a meter. So meters, originally, a meter was supposed to represent, all the way around the circumference of the Earth would be 40 million meters, 40,000 kilometers. And then there was a bar made out of platinum and iridium in some science institution in Paris, France, and they had the meter stick in there, and that was the official meter stick, and it had to be measured at just exactly the right temperature. But now any lab can, apparently, any lab can get out their light measuring devices and use this to calibrate any kind of measuring equipment. They can determine on their own what a meter consists of. So the speed of light is now defined as exactly 299,792,458 meters per second. Now, that raises the question of how is the second defined, and I think we're using atomic clocks for that, right? Anyway, we have these really precise measurements of seconds, and from that, we're able to define the meter as being the length. This many meters is the exact length that light travels in 1 exact second. Okay, so that's now considered an exact number. Now, of course, there's still a little uncertainty in those measurements. As the measurements get better and better, what that will do is it will fine-tune our measurements of what a meter is the intention. Okay. All right. Now, a lot of times we use this approximation 3.00, but remember, it's not exactly 3. It does round to 3.00 to 3 significant figures, but beyond that, the digits are different. All right, let's get to talking energy transfer. I'm going to say that's the most important part of this entire chapter. So a lot of the stuff that we've done so far is just building an understanding of what light is and what the propagation of these electric and magnetic fields corresponds to. But now what we want to do is concentrate on how much energy is carried by these electric and magnetic fields. And so what we're going to do is we're going to go back and say there's an energy density in propagating electric and magnetic fields. And those formulas that we've developed along the way, we introduced electric field energy density back when we were working with capacitors. We introduced magnetic field energy densities back when we were looking at inductors. So the inductors and capacitors, we worked from these formulas. Now the book worked from these formulas because this is epsilon naught and this is mu naught. But what we've been doing in class is just using little k. So I'm going to go back and use those. But it's worth pointing out that the combined energy density comes from looking at all the energy stored in the electric field components and the magnetic field components. That's where we're headed with this. Okay, so here's our picture. What's going on here is I've got this propagating electric and magnetic, these propagating electric and magnetic fields, and what we're going to do is we're going to draw a line, and we're going to dare the electric and magnetic fields to cross that line, and of course they do. And what we're going to say is that in a volume of space, and that volume is going to have some kind of a cross-sectional area. So I'm going to define a cross-sectional area. Maybe it's a meter square or something convenient. And then as time goes by, the energy stored in the field propagates at the speed of light. So that energy travels a distance dx during a time interval of dt. So that energy is making its way through space. And I guess that's everything we need on this slide. So as that field propagates, energy is being carried along. And what we can do is we can come up with what we call intensity. So there is energy transported through a unit area in a unit amount of time is called the intensity. Now the book is going to use the symbol S for intensity, and that's because it's kind of conventional to do this. When we're first learning about propagation of electric and magnetic fields and the energy they carry, we start by calling this the Poynting vector, named after somebody, and we use the symbol S. So for chapter 31, we use the symbol S, but in chapter 32 and beyond, intensity becomes capital I, which is not the same thing as current, so don't get confused by that. So anyway, they're going to use S for now. I'm going to just start using I right away. But the intensity is equal to the energy per time per area. So how many joules, if we go back to this picture, this is a good picture. Here we've designated a region of space, and during 1 second, how much energy passes 1 square meter? And that's a designation of the intensity. So if there's more energy concentrated into that area, and there's more energy per time, that is a more intense energy source. Okay, now there's a bunch of equations like this that they go through in the book. You are welcome to use those. But I'm gonna suggest using a different set of formulas right here. And so I'm going to say here is light propagating. It consists of these electric and magnetic fields that are all mutually perpendicular. I'm going to go back, and for energy density, I'm going to write that as 1 over 8 pi k E squared, 1 over 8 pi k CB squared, and show that, I hope very clearly, that the energy storage in the electric fields and the energy storage in the magnetic fields match. So I'm using the same formula they did at this point, saying that the combined energy density from the electric field components and the magnetic field components can be combined to give the total energy density. Now the intensity consists of an energy density times a velocity. And that is a formula that can be derived from this picture. What we're saying is, let's stop the picture, let's freeze it, and then what we're going to do is we're going to calculate the energy at a given instant within this volume. And then what we'll do is we'll say, what's the intensity given by? Well, the intensity means that all of the energy that was on this side of the boundary during the next instant is going to cross the boundary. And so there's a factor of velocity that comes into it. It's like, here is the energy density. We've frozen the picture. Now how do we turn that into an intensity? We just multiply by how fast it's moving. Okay, so the first set of formulas are determining the energy density based on what the electric and magnetic fields are. Now for acceleration fields, E and CB have the same value. Go back and look at those formulas that we have written down 3 or 4 times now, I guess. I'm making a big deal about this. But the E and the CB will match for acceleration fields, and the energy densities will also match. So this is like half the energy here, half the energy here, this is the total, and then the intensity comes from taking the total energy density, energy per volume, multiplying that by C. So let's just put some numbers in. Let's say that we're in a region of space where the electric field, it's an acceleration field, and the electric field there is 60 newtons per coulomb. So if the electric field is 60 newtons per coulomb, so is the magnetic field once we multiply by C. So E is equal to 60 newtons per coulomb, CB is equal to 60 newtons per coulomb. Now in parentheses, I converted back to Tesla to show that, yeah, I can write it down in terms of Tesla. So that's 20 microtesla. But the energy densities will match. So both the electric components and the magnetic components for these numbers end up with the same amount of energy per volume. And it's worth staring at the units here. This is some number of joules per cubic meter. I can add those together, which just involves doubling it. And then from that, I can get the intensity. So the intensity, this is what's interesting with electric and magnetic fields. This is what's interesting, I think, with energy being carried by light, is that when we do the calculations, we tend to get these tiny, tiny energy densities. We go, really? Like, there's a cubic meter of sunlight or something, and it contains just a really tiny amount of energy. But when we calculate the intensities can be pretty significant. Now, this isn't sunlight. Sunlight has like 100 times that. The sunlight reaching the Earth on a nice sunny day is probably 1,000 watts per meter, not 10. But in any case, the intensities tend to get, are much larger, and that's because it's coming in so fast. We say how much energy is in a cubic meter, not so much, but 300 million of those cubic meters are going to reach us every second, okay, and land on a 1 square meter section of the ground. And so the intensities can actually turn out to be quite large. Okay, we're kind of halfway through this, so I'm going to say this is a really good set of formulas to work from. Now, the rest of this looks like, let's go back. If you remember, for acceleration fields, the electric fields are given by kq over r, a over c squared sine theta, so is c times ba. So what we can do is we can algebraically write down what the energy density is for the electric fields coming off of that charge, and it's going to be given by 1 over 8 pi k squared, q squared, so it depends on how much charge do we have, and it depends on what the acceleration is, squared, and it depends on sine squared theta. So all of those factors are coming into this. Now, once we've calculated the energy density due to the electric fields, we know that the energy density due to the magnetic fields is the very same expression. So that's done, taken care of. So here's our charge, and it's accelerating right along the x-axis. And so what this formula is telling us is that, okay, I've finished down here, and then I'm coming back here. And what I've done is I've taken everything that we've looked at down there, and I just added these two together. So I'm adding together, I think we got, I'm just checking the factors. If you guys catch any mistakes, definitely let me know, and I'll get those corrected. Okay, so it went from 1 over 8 pi to 1 over 4 pi because we included both contributions. So that says that the intensity, which is U times C, is 1 over 4 pi k q squared a squared over c to the third power, because I multiplied by a factor of c. Now this is, I'm going to say, the interesting part. Sine squared divided by r squared. So the intensity of the light coming away from here is dropping off like r squared. Well, the surface area is increasing like r squared. So that's telling us that the energy is being conserved. The energy is conserved as it spreads out away from that point source, and that's what gives us a net flow of energy away from that charge. So the intensity is dropping off like r squared. That's what we've seen before, where we have a central source of energy being radiated. Also, what's interesting is there's a sine squared factor. So sine squared says that how much of this energy is going directly forward? Basically none. So if I have an accelerating charge, at least in the direction that the acceleration is taking place, there's no electromagnetic field propagation in that direction. Now when I look away from the direction of acceleration, I start to see higher and higher intensity. And that intensity will be the very largest at 90 degrees. So if I'm a charge accelerating through space, most of the energy that's radiating off of me is going off in directions that are at 90 degrees compared with the direction, relative to the direction of my acceleration. Okay, so that's what this is going to look like. So I hope that was worth going through. Again, I don't see any of this stuff showing up on our midterms. I think the stuff that you guys want to be good on, let me go back and point to this. I think this stuff. So you guys definitely need to be, and you'll see homework problems for this too. You definitely want to be able to, starting with electric and magnetic fields, work your way through the energy densities and intensities. Or, as you might expect, if you are given the intensity, work back through the energy densities and the fields from starting from the intensity. So you should be able to work forward and backwards through these energy equations. I feel like these are really good for building some intuition about the properties of light. So let's get back to this formula now. This, I'm going to say, I think you guys are at the point where if you stop and think about this, here's the acceleration, not much energy going here, lots of energy here, not much behind. So it's kind of symmetric between forward and backwards directions. The intensity is behaving like sine squared theta over r squared. Now I'm going to go ahead and ask, if this is what the intensity pattern looks like, what's the rate, the total rate of energy being radiated? What is the power of an accelerating charge? At what rate is it radiating energy away? And this is a little bit beyond what I would expect to do in the course. So very quickly, if we take this formula that we've developed on the page before, if we take this intensity formula and we integrate over all possible angles theta, what that consists of is integrating over a spherical surface. And I'm not going to go through the details. It turns out that each one of these little differential pieces of area We can write down a formula for that. Anybody interested, definitely stop by office hours and we can go through this. But I just want to show that this definition of D area works, because if I go through and integrate over all the angles, I get the surface area of a sphere. Okay, so it definitely works. So let's take this dA, and what we're going to do is we're going to take our intensity formula and we're going to integrate. Now the r's in this are actually constant. So I'm not integrating over different distances. I'm just picking one spherical boundary and then adding together the intensity at each location along that spherical boundary. I'm keeping track of all the energy as it spreads past that boundary. When we take that integration and carry out the integration, what we end up with is the power, the rate at which energy is crossing any one of these spherical boundaries is the same, because the r squared in the intensity the 1 over r squared in the intensity is canceling with the r squared in the surface area of that sphere. So the r squareds cancel out, and it says, yeah, if I follow this energy from one spherical shell to the next, it's the same amount of energy at every spherical shell. I am not losing energy along the way. The energy is conserved. And that tells us that the energy is propagating away consistently from that central source. Now the angular dependence, when I've integrated over all possible angles, and remember most of it's going off to the sides and above, most of it's going off in the region around 90 degrees, not much in the front, not much in the back. But when we add all that together, when we integrate all that, what we end up with is a total radiation rate, a total power of 2/3 kq squared, so it depends on the charge, how much charge we have, squared. It depends on what the acceleration is, squared, and it depends on the speed of light, 1 over the speed of light cubed with a factor of 2/3. So we could plug numbers into that and say what is the rate at which an electron is radiating away energy if it's accelerating like this. Okay, let's look at some examples with some numbers. I think what we're going to start with here, example 31.6, we're going to look at the electric and magnetic fields of the light that's reaching us from the sun. Okay, so here is some starlight coming in from the sun. And what it says is we're actually not going to wait for the light to reach the Earth. We're actually going to go up above the atmosphere. So if we go up above the atmosphere, what we measure for sunlight is 1,350 joules per second per meter squared. Those are intensity units. So 1,350 watts per square meter, and then it says assume that this is a single electric magnetic field propagation. Oh, I see. So typically the way we think of sunlight is that sunlight doesn't have a consistent orientation for its electric and magnetic fields. And so what's happening is the light coming in, it doesn't necessarily have, the E field's not lined up exactly in a particular orientation from one location in space to the next. The orientation of the electric and magnetic fields of the light is kind of random, and that's why we don't, sunlight coming in does not have a consistent direction to its electric or magnetic field. Okay, so we can't generate a current off of just the sunlight itself, the electric fields in the sunlight. We can certainly get solar panels and use the energy of the photons to boost the electrons into excited quantum states, and so we can build solar panels and definitely generate some voltages that way. But let's think about what this says then. So let's work back through the formulas. Now the intensity coming in, that needs to be treated as an average value, 1,350 watts per square meter. I can pretty quickly divide that through by C, and that's going to give me an average value for the energy density. Now, everything we do here is going to be in averages and RMSs. So once I get this for the average value total, I can say that half of that energy density, is associated with the electric fields, and half of that is associated with the magnetic fields. So we're just kind of doing bookkeeping here on how much energy do we have stored in this electric magnetic field that's propagating towards us. And then once I have the energy densities, I can plug into this formula. This is the formula relating energy density with electric field. Now some of these formulas are turned around from what we presented earlier. That shouldn't be a problem, right? So we can come back to here. So these formulas, right? So what we've done is, this is now being given in the example we're working on, and we're solving for E and CB, so I'm multiplying by 8 pi k, taking a square root, to find out what the electric field will be. And doing that, it gives us an electric field of 713 newtons per coulomb and a magnetic field of 713 newtons per coulomb. Now we had mentioned this earlier. See the intensity? That's a good rate at which energy is coming in. I mean, if you sit out on a nice sunny day, you can feel that, right? So here is the rate of energy coming in. That looks pretty large, but the energy densities are really small. And it doesn't take a lot of energy density to create a lot of intensity because the sunlight's traveling so fast. On the other hand, the fields, the electric field value and the magnetic field value, those both look like pretty good sized numbers, right? 713 newtons per coulomb. And then, I went back in and put the magnetic field, RMS magnetic field, also wrote that down in terms of Tesla. Okay, so that's what the fields would be. Now, a second part of this question, I think, did we add this in or did they? I think we added this in. I added it in. Okay, it was me. I added it in. And so what we want to do is say, what would happen if this light runs into something and it's perfectly absorbed? If it's perfectly absorbed, how much force would the sunlight exert on an object? And your first response might be, what do you mean force? Sunlight doesn't exert forces on things, but it sure does. We really can exert forces using light. And so what we can do is we can say, same thing we used back in chapter 9, the force has to do with how much momentum, the rate at which momentum is being transferred into an object. So if the sunlight hits and it's perfectly absorbed, then all of the momentum that was in the light has now transferred into that object, and that will exert a force. Now, with light, we're going to see in a few weeks here when we do special relativity that for massless particles, photons are massless, the momentum of photons is equal to their energy divided by c. And so the force now can be written as 1 over c times du dt. We've switched from writing this in terms of momentum to writing in terms of energy. And that says that the force can be written as 1 over c times the power. Now remember, what we said here was the light is being perfectly absorbed. All of the momentum is transferring into that object that's absorbing the light. Now, that object also is taking in 1,350 joules every second for every square meter, but now we've moved on and asked, what's the force? And that's going to be in terms of momentum, and that's going to get divided through by a factor of c. So the momentum question is going to give us a very different answer. The power can be written as intensity times area. So let's do this. Let's say that we have a roof. I'm going to say it's, 8 meters by 12 meters. Oh, that's kind of like my house. So I've got a roof here, and it's 8 meters by 12 meters, and it's got a total area, it's covered with solar panels right now, but it's got a total area of 100 cubic meters. Well, it's not completely covered. I wish it were more covered. I put as many solar panels up there as would fit. Or I had as many solar panels put up there as would comfortably fit. So anyway, 100, that's supposed to say square meters. I have no idea why it says cubed. I should get that changed. Anyway, that's square meters, 100. Oh, and then I dropped it here. So I put an extra power of meters over here. This needs to be 2 powers of meters. That needs to be 2. Take one of the meters from there and move it over to here. Okay, not good. But anyway, the area here is 100. So the power coming in is going to be the 1,350 watts per square meter. That's what the power was. It's I times area, and that's 135 kilowatts. Wow. If I could get solar panels up there so that they were tipped facing right towards the sun, that's part of the heart. That's one of the difficulties. And absorb all that light on a perfectly sunny day where the atmosphere is, this is above the Earth's atmosphere too. I could get 135 kilowatt of sunlight energy reaching, and then the solar panels are like maybe 8 or 10% efficient. Anyway, the force from the formulas here, plugging that in, I have to divide through by C. The force is 450 micronewtons. That's not very impressive, right? We really don't have very much in terms of the force. Hitting the roof. So I'm not so worried about the roof collapsing because of sunlight. Now other things could collapse the roof, but sunlight looks like it's not going to exert much in the way of forces. Okay, so this is the formula we just went through. Now let me go back here and ask another question. What if instead the roof were perfectly reflecting? Because if it were perfectly reflecting, then we would have the light coming in transferring all of its momentum, but by bouncing off the roof, that would double the momentum transfer. That would take twice as much force to have the light completely stop and then reverse direction and head right back out at the speed of light. So if it was perfectly reflecting, that number would be doubled. Okay, 450 micronewtons for bringing the light in and being absorbed, 450 micronewtons for sending the light right back out again. And that's what these formulas are discussing. All right, I think this is the last example that we have. I know I always say that, and then there's 2 or 3 more examples. But if this sunlight is really exerting a force, could we use it to propel a spacecraft? Could we get a spacecraft sent out and operate it by just getting a big sail and having sunlight hit the sail? So here are some of the proposals. It's saying what we want to do is we want to build a big solar sail. And we want it to be 1,000 meters by 1,000 meters. That's really big. So we're going to have to figure a way to make it really compact and then get a rocket and boost it up above the atmosphere. And then once we're safely above the atmosphere, somehow you have to unfold this sail, and you have to make the sail kind of rigid, right? Something's got to hold the sail so it's not just flopping around out there. Let's make it highly reflective. That gives us that factor of 2 we talked about. And then it says, by how much could this increase the speed of a spacecraft in 1 year? So the spacecraft is going to be started from rest, and how far would we be able to get in a year? So let's take a look and see. So here's my picture. Here's the sun. Here's the Earth. Here is the spacecraft. Here is how much mass it has. Here is that big solar sail. And the area for the solar sail is 10,000 by 10,000 kilometers. And let's see. Oh, that's the bigger sail. This is my upgraded sail. Let's go back over and look at the original numbers. So originally we said the spacecraft is 5,000 kilometers. We started out with just 1 kilometer by 1 kilometer. So 1 kilometer by 1 kilometer gives us 1,000,000 square meters. The intensity of the sunlight, let's say that the spacecraft is starting not in orbit around the Earth, but let's put it out here somewhere. So it's the same distance from the sun that the Earth is. So it's going to start out with an intensity of sunlight, 1,350 watts per square meter. Now the force we're going to get, we're going to pick up that factor of 2 because this is a perfectly reflective solar sail. And on the previous examples, we had gone through and shown that the force can come from measuring the intensity times the area, that's the power, divided by c. When I put all those numbers in, this was pretty discouraging. So if I have a solar sail that is 1 kilometer by 1 kilometer, that's big, right? And I turn it and face the sun, and it's perfectly reflective. I am only getting 9 newtons of force. Okay, now 9 newtons doesn't sound like much, but even if we have a low acceleration, if we continue to accelerate even at a low rate, once a few days have gone by or a few weeks, or, you know, most of the problems where we've done accelerations, we only let the accelerations last for a few seconds. What if we just let the acceleration build on acceleration, build on acceleration? How fast could we get the spacecraft going? So 9 newtons, maybe that's enough to work with, but wait a minute, what about the force of gravity from the sun? So the mass of the sun, did I write it down? No. All right, the mass of the sun is 2 times 10 to the 30th kilograms. So what I did was I ignored Earth. I figured once the solar sail satellite heads out, it's not going to be that close to Earth. Once it gets a little ways from Earth, the dominant gravitational object is going to be the sun. So it's really going to be the sun's gravity that determines how far out into the solar system or how long it's going to take to get out into the solar system. So I put in the mass of the sun and the mass of the spacecraft and the gravitational force constant, and then I put in, boy, I hope I did this. Oh, I did, okay. So big R is the orbital distance of the Earth, and then little r is a variable. So the way I set this up was I said I'm starting from Earth's orbit, I'm launching a spacecraft out so that it's in the same orbit around the sun as Earth, but it's no longer close to the Earth. Far enough away from the Earth, maybe it's over here. So it's far enough away from the Earth that the sun's gravity is the dominant effect, so we'll just ignore Earth in this. So we're going to start at distance big R, and then we're going to try and get out to little r. Now what I found was, for this satellite, at the location of Earth's orbit, the gravitation is exerting a force of 30 newtons. Okay, that's a problem. The sunlight is only exerting a force of 9 newtons, but gravity from the sun is exerting a force of 30 newtons. So we need a larger sail. And that's when I did this. So I said, let's make this sail 100 times bigger. So I made the sail 10 kilometers by 10 kilometers. Now remember, we have to be able to unfurl this sail, and we have to have a rigid structure where we can maintain the shape of the sail, but if that's going to be possible, then the sunlight now is going to get a boost by a factor of 100, and now the sunlight's going to be 900 newtons, gravity is only 30 newtons, so I'm going to have sunlight in one direction, I'll have gravity in the other direction. That's going to give me a net force of 870 newtons divided by the mass of the spacecraft. At least initially, my acceleration is going to be 0.174 meters per second squared. Now again, that looks like a small acceleration, but the problems that we're used to looking at with accelerations, the accelerations only last for a few seconds. And this time, the acceleration just lasts 24/7. You know, the acceleration is just constant. And so we can actually pick up to have some pretty high velocities. So if this were to last for a year, if we had this acceleration just steady for a whole year, a year's like 30 million seconds. So what would that be in a year after 30 million seconds? And we would be traveling at a really high speed. I want to say 30 to 10 million. So we could be 1,000,000 meters per second. You know, we could be going really, really fast. Now, what I did, and you guys don't have to worry about this, but what I did was I went in and I thought, what if we went out to Pluto? What if we sailed to Pluto in this spacecraft, this completely impractical spacecraft with a sail that's 10 kilometers by 10 kilometers. Pluto is like 40 Earth orbital distances, so I have to go 40 times as far away from the sun. But what I realized is that the sunlight is dropping off with distance like r squared, and gravity is doing the same thing. And so as I get farther and farther away from the sun, I'm going to continue to get this effect from the sunlight. And so I calculated how much work I would need or how much work I would get from the sunlight heading out there, and I'm trying to remember where. I don't remember if I've got that gravitational stuff included. Okay, so here is the force that we're using from the sunlight acting on the, I guess I just used the 870 newtons. So if I continue with the 870 newtons and I integrate this all the way out, I end up accumulating 1.3 10 to the 14 joules of kinetic energy. Now if that's the amount of energy that the solar sails have absorbed, the kinetic energy at 1.3 10 to the 14th joules would give us a speed of 230,000 meters per second. Okay, and if you run the numbers, I'm not showing all the details here. We could be to Pluto in a matter of months. So starting out with these very modest accelerations, but keeping the acceleration going non-stop, actually you pick up some pretty good speeds, and you can move yourself through the solar system pretty quickly. Again, the problem here is, how do we get that solar sail built so that it's sturdy, it's lightweight, so that we can move around the solar system pretty easily? Okay, I think I am going to end right there. Here is the radio communication showing how we encode information in either the frequency or the amplitude of our radio signals, and then we're into the summaries. Okay. All right, so I'm going to stop there. I think we've hit all the topics. Again, the most important stuff from this chapter is being able to do all of the energy calculations for those electric and magnetic fields that are propagating. So if you guys have any questions on anything, definitely stop by. Let's take a look and see if we can figure out your questions.